I would like to thank to the organizers for inviting me. Yeah. My topic is restriction estimate. I think in this workshop, maybe I am responsible for harmonic analysis part. I think. Yeah, I'm the only speaker about the topic about harmonic analysis. So in this talk there may be no PD equations or but I want to talk about I want to focus on the restriction estimate for space curves, but I want to talk about the more general situations such as surfaces or some submanifolds of codimension 2, which has some applications to the PDEs. So first I will talk about the restriction estimate, restriction of the Fourier transform on the curves or hypersurfaces or some submanifolds, and then some applications that I know is some mass concentration phenomena and the unique continuation property. So let me start from the restriction of the Fourier transform. Here's the basic properties of the Fourier transform. If f is in L1, then the Fourier transform of f is a continuous function vanishing at the infinity. So it is easy to see that this estimate, L1, L infinity estimate, and then by Plancher's theorem, if f is in L2, then we can see that the Fourier transform is an isometry in the L2 space. Then by interpolation, we can see that the Hausdorff-Young inequality, and then actually this is the best possible estimate in the RD. So the restriction problem is we want to restrict the Fourier transform on some submanifold. It's a major zero set. So here's the operator of the we call restriction operator, which is defined by this. Is the Fourier transform is restricted on some compact submanifold M, and it carries with some measure on M. So the question is for which M and for which P and Q this estimate holds. So again, this some trivial estimate is L1 L infinity estimate is trivial estimate, but generally this estimate fails because the M is major zero set, so there is no meaningful way to restrict if f is L2 function, then the Fourier transform of f is also L2 function. So there is no way to we always construct this quantity can blows up. So the question is we can guess that P will be between 1 and some P0, and then the P0 will be determined by the M. Actually, it depends on some coverage condition on M. So the first example is the M is hyperplane. In this case, the P equals to 1 is the best possible. That is the only estimate. And then if M is some hypersurfaces, then there is here is the two necessary conditions. P prime is bigger than D plus 1 over D minus 1 Q, and P is less than 2d over d minus 1. These are necessary conditions. And then the restriction conjecture asserts that these conditions are also sufficient. Yeah. And then if M is a submanifold of codimension 2, then there is only some kind of Thomas Stein type estimate only is known. So yeah, here is some quantities. Yeah, that is the only things. And then if we choose M is a space curve in RD with non-vanishing torsion, then this operator can be written as like this. In this case, it is well known that these conditions are necessary and sufficient. Yeah. So yeah, let me give some more details about the space curves. Usually we estimate some kind of this is actually dual form of the restriction operator. So we investigate this operator has some kind of decay beta. So we want to find, the aim is to find out the optimal PQ and the decay rate beta. So and then it is well known that the decay rate and P and Q is affected by the torsion condition of gamma. So this condition tells gamma is non-degenerate curves. So this quantity is the torsion, kind of torsion of gamma. Yes. So it is well known that beta is d over q is optimal whenever P and Q satisfying these two conditions. Yeah. So in the non-degenerate case, there is a lot of results from 1970s. They proved for two-dimensional case, and then for higher dimensions, if gamma is the moment curve, then Prestini, Christ, or Drury obtained some results. And then if we also consider more general situation, replace x dot gamma t by some function phi on x and t. This we call this this situation is variable coefficient, and then this condition is also some torsion condition on this function. So there was also some results by Bach and Lee, and Bach, Oberlin, and Seeger obtained some weak type estimate at the endpoint. Yeah. So usually when d is equal to, there is no endpoint estimate, but the higher dimensional case, they found that there is a weak type estimate, and then that estimate is very sharp. Yeah.
What do you mean by that?
Yeah.
So the Lorentz exponent cannot be lowered.
Yeah, Lorentz exponent cannot be improved. Yes. Right. So yeah, there is so and then we consider monomial curves, such as gamma t is t to the a1, t to the a2, then t to the ad. In this case, if a1 to the ad are just distinct positive integers, then Christ obtained some, under this condition of P and Q, they obtained some restriction estimate. but these depends on the A. Yeah, and then this quantity is always bigger than this optimal quantity. So the question is, how can we obtain a uniform estimate for degenerate curves? Here, uniform estimate means the estimate, the restriction estimate does not depend on the A1 to AD. So the answer is use the affine occurrence measure, WT dt, instead of the just Lebesgue measure, dt. This quantity is torsion and to the some power. Yeah, this gives a uniform estimate. So actually the affine occurrence measure is invariant under some diffeomorphic parametrization, and this measure compensating for degeneracy of gamma, because the degeneracy means the torsion of gamma vanishes, but on the point that gamma vanishes, this affine occurrence measure also vanishes. So the role of the affine occurrence measure is that. And then by affine occurrence reparametrization, the new curve gamma S has a non-vanishing torsion always. Yeah. So by using this, we consider this modified oscillator integral. So there is some results for when d is equal to 2, then Scholin and Soap obtained some kind of this estimate. And then for monomial curves, Chris Drury and Marshall and Park, Oberlin, Siegel obtained some results. Park, Oberlin, Siegel also obtained the weak type estimate at the end point. And then for polynomial curves of simple type, curves looks like defined by these. The last exponent is only PT. In this case, one can see the weak type estimate at the end point. And then finally, the polynomial curves. For polynomial curves, the Andrinos Wright and recently Stover obtained the optimal estimate. So here is the more general estimate. Look at this estimate we replace the Lebesgue measure by the general measure, mu. Which is, mu is just positive Borel measure of dimension alpha, and then gamma is just non-degenerate curve. Then we can obtain some kind of decay estimate. The decay is changed to from d over q to alpha over q. Under these conditions, beta alpha over q plus 1 over p is less than 1, and then this q is bigger than beta alpha plus 1 is related to these conditions. Actually, the beta alpha is defined by just this j plus 1 alpha plus d minus j minus 1 times d minus j over 2. This is if we sum from 1 to d, then we obtain the d plus 1 over 2. But in this case, if mu is alpha dimensional measure, and alpha is between d minus j minus 1 and d minus j, then we just sum until from 1 to d minus j minus 1, and then just give alpha, then just sum from 1 to alpha, then we obtain the beta alpha. Yeah. So this quantity d plus 1 over 2 is arises from on the here d plus 1 over 2. Yeah. This is replaced by the beta alpha. If we choose more general, if we consider more general measure mu. Yeah. So, and then there is another more estimate for the finite type curves. It's a more general situation. Finite curves is satisfies for some a1 to ad positive integers. This determinant non-vanishes. Then using the sum, this is an analog to the affine occurrence measure. We just replace the d plus 1 over 2 is by beta alpha. So using this weight, you can see this estimate holds for of the decay lambda to the alpha over q. Yeah. So So how this alpha over q is from the just the simple change of variables, and then here is the operator. You can change the lambda x to the just y, change of variables, and then using the mu is alpha dimensional measure, it is easy to see that the lambda to the alpha of q is optimal. And then we can find the necessary condition about the p and q. If this estimate holds, then you can obtain the beta alpha of q plus 1 over p is smaller than 1. So to see this, just fix some alpha. The dimension alpha is fixed, and then choose the measure mu is in such a way using the Dirac measure, and then the rest of the exponents like this, so that we obtain this measure mu is alpha dimensional. Yes. Then f, we choose f is just characteristic function from characteristic function on the interval 0 to lambda to the minus 1 of d. Then the LP norm of f is just lambda to the minus 1 over dp. And then if this is a this is a standard argument to obtain the necessary condition. So if when xi is smaller than lambda to the minus 1 plus I over d, then this operator has a row bound of lambda to the minus 1 of d. So we see that this norm is this norm has a row bound of lambda to the 1 over d and mu r to the 1 of q. here the R is a rectangle of dimension is from this. X1 is lambda to the minus 1 plus 1 over d, so this dimension, and then this dimension is the dimension of xd, so we can construct this rectangle. Then we can this rectangle is some this dimension is very short, but this dimension is very long. So we cover this rectangle by balls of radius lambda to the minus 1 plus j plus 1 of d. This why the reason why we choose this radius is from the dimension of alpha. We fixed the dimension of alpha is between d minus j minus 1 and d minus j, so we choose this radius. So this rectangle. So the radius is bigger than some dimensions. So the number of balls is like this. Until this dimension, we just only one balls cover the rectangles, and then for the rest, we need some more balls. So the mu measure of R is like this. The number and the measure of balls. So we obtain this is the definition of beta alpha. So so combine these three estimates. Combine these three estimates, we obtain the this quantity. So if for any lambda is bigger than 1, we obtain this inequality. So this is the necessary conditions. And then we move to the case of hypersurfaces. This is I just want to introduce some well-known results for the hypersurfaces. This is the very famous theorem by Thomas and Stein. They obtained some Fourier restriction estimate, LP, L2 estimate. This condition, P is between 1 and 2d plus 1 over d plus 3 is necessary and sufficient conditions. Or equivalently, this estimate is called just extension estimate. With this operator, F, the sigma hat is defined by like this. This is this operator is important in some PDEs. So if M is a paraboloid, then the we can write the extension operator as this. F d sigma to the x times xt is can be written as e to the 2 pi I x dot c plus t c to the squared. Actually, this is the exactly this is the solution of a free Schrödinger equation with initial data f. And then the restriction conjecture tells that if M is a compact hypersurface with non-vanishing Gaussian curvature, then this estimate holds when LR estimate holds when R is bigger than 2d over d minus 1 and S prime is less than d minus 1. plus 1R. Here's some recent, the latest results for restriction conjecture for the paraboloid in R3. Yeah, I just drew the only R3 case. So here is the Thomas time obtained this estimate, and then the latest result by Bourgain and Goose. Yeah, and then the dark area is the conjectured range. Well, so there are still a lot of areas remains. Yeah. The extension, as I told, the extension operator, this is the solution of the free Schrödinger equation with initial data f. So Schrödinger equation is the solution of Schrödinger equation is related to the restriction operator on the paraboloid, and then wave equation, for the wave equation, the solution of wave equation is related to the restriction estimate on the cone, and the Helmholtz equation is related to its phase is unit sphere. So here is an application that I have learned is the mass concentration phenomena. Consider the L2 critical nonlinear Schrödinger equation. The mass concentration phenomena says that if U, the solution U, blows up at the time t max, then there is somewhere we don't know the exact location, but there exists in somewhere the mass of the solution never vanishes. Yeah, this is the mass concentration phenomena. If we consider some kind of non-elliptic Schrödinger equation, then there exists. Then this ball should be replaced by the rectangle R with the diameter. The magnitude is the T max minus T. Yeah. So here is results from Bourgain, and then they the first line they obtained some mass concentration phenomena for the Schrödinger equations, and then there also exists for the higher order Schrödinger equation, and recently fractional Schrödinger equation they proved that there exists a mass concentration property. And then for the two-dimensional non-elliptic Schrödinger equations, there is also results. And then there is no results about the higher dimensional non-elliptic Schrödinger equations. So yeah. And then these results rely on refined Strickhatch estimate. So here is done. This is one example of the refined Strickhatch estimate. So this theorem is by Begot and Vargas. This theorem tells that the solution of the Schrödinger equation in the LQ space, it is bounded by this quantity. In fact, this quantity is less than the L2 norm of F. So this quantity is first F is first integrate on the dyadic cubes. On dyadic cubes we integrate F with LP, And then here is the some weight, and then we choose the small AQ. Then this is this makes the mass concentration phenomena possible. So yeah, and then actually this refined Strickhatch estimate follows from some bilinear restriction estimate. So here's the result by Lee and Vargas. It looks quite complicated, but this operator EI is some extension operator on Cauchy phi Cauchy. Yes, and then if there is some transversality condition under this transversality condition, we can see that this bilinear estimate. Yeah, from this using the Fittini type decomposition, then yeah, you can obtain this refined Strickhatch estimate. Yeah. And then, yeah. Yeah. Finally, we see the restriction of the Fourier transform to some submanifold. Yeah, just let me give some notation. Here's the M is the zeta, phi 1 zeta, phi 2 zeta is a compact submanifold in RD of codimension 2. And then there exist some vectors normal to M. We denote it by theta. Then you can consider the inner product of theta and the phi 1, phi 2. Then this quantity is the Hessian matrix of second derivative of the mapping. This zeta to the phi 1 zeta, phi 2 zeta. Then here's the theorem. Is a kind of Thomas Stein type estimate. Yeah, this theorem holds if and only if there exists some k less than d over 2, such that for any unit vector theta, this is some kind of non-vanishing Gaussian curvature. This condition is related to that non-vanishing Gaussian curvature condition. So Michael Christ obtained this condition is necessary, and then Morkenhaupt proved this condition is also sufficient. So using this estimate, the Carly obtained some kind of Kaleman type estimate. If the PD is an elliptic partial differential operator of order M, then the direction of the characteristic is nu. Then here is Kaleman type estimate. This can be proved by the restriction estimate for the submanifold of codimension 2. Actually, she calculate this estimate can be transformed to the restriction estimate, and then the phase, the manifold is the intersection of the cone and a cylinder. She proved this Kaleman type estimate, and then by using this, she obtained some kind of strong unique continuation property related to the elliptic, some kind of differential inequality P with some potential. Then So yeah, this is an application of restriction estimate for some manifold of codimension 2. So yeah, she claims that she is the first one that used that to prove the Kaleman type estimate from the restriction estimate. Yeah. I think stop here.